It's literally all talk in prison now. In jail, rather. Because look, he didn't continue. I fucking hated that about jail. They were all fucking pussies. Mhm. Johnny smokes hot rod.
How are you doing? Your boy. With your boy you get in a fight with?
No, I ain't messing with him.
What was that all about?
A girl.
Oh, huh?
Yeah.
This guy, young kid, Gerard, they call him Hot Rod, and he just got in.
Trump or something.
As you get into fights over the stupidest shit.
Ain't number $10. But still, that's the principle. I don't need to give about the $10. That's the principle, man. You play me out of the league.
Most of the fights in jail are because you didn't pay your debt. The inmate don't look at it as the debt not being paid as much as it's a lack of respect to them.
Shut up. This, he said that I didn't have a 4 days hit stronger than the one you gave her.
I hear it go straight back to bed.
Hell no. Go on, brother.
Can't even see the fight.
It was like at 3 in the morning. I was knocked out, and next thing I heard, boom, 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 boom. And Shekels was just whooping his ass in that shower, and it was.
Is this GP or PC?
It's kind of scary because I was like, I regret.
What does this guy think of criminal justice now? It's like, this is literally every single jail.
Taking a remote from Shekels, I could have actually been the one who got stumped out.
As a police officer, I'm sworn to protect. So it's just hard to stay focused and in character.
I didn't even get to do what I want to do to him. Let him go, Eric.
Let him go.
Oh. They have cameras, you fucking idiot.
I don't know if the guards know. They don't act like they have any clue that anything exceptional is going on.
This down here getting stumped out in the shower, and they go to the wrong room. At that point, I was like, I don't think nobody gonna protect me in this. And the dude didn't snitch or nothing. He just went to his front, laid under his cover, tried to hide it. And me, I didn't want to. Hey, CO, the guards obviously don't give a about what's going on in here.
Well, I love that.
The Clark County Jail has an extremely antiquated camera system, and the officer can only see one section at a time.
What a
Makes it hard
terrible
for them to do
system.
their job to the best of their ability. Makes it tough for me too.
I got him. I got to. Charlie, come here. I'm gonna thump him all the way out. I'm gonna beat him up every day till you go or you pay up what you up. Oh man.
Is this guy who got beat up? I like how nobody just knows how to fight.
You wrong, bro. Never done a damn thing to you.
So basically, you calling a lie.
I'm definitely calling somebody a liar, yeah.
That guy's got balls. I respect that. He goes back in there.
It got real serious, and I was just like nervous. I was like,
I'm gonna beat you up every single day.
Don't get on the butt. I ain't getting on no butt.
Oh, it's cheap of you.
On the spot. The morning time you go get your turn, smack it as you can, I'm gonna smack it.
seeing Shekels reminded me of being in Detroit. I had a cousin who was killed right on the corner of our block. It was pretty rough just, you know, seeing all that stuff.
Now my son's out, I'm gonna send him down the stretcher tomorrow.
They're just cool. But if you cross her,
So, from what I've seen, female fights, there's a lot of hair pulling and a lot of kind of yelling. So we'll see what we got.
she will get in your.
How you doing?
So I woke up this morning, go to the salon or whatever. I just hear this on talk correctly. I don't know what's cranking this bitch up, making her think she gon' beat my ass. So Pope all play it. It's about respect. She keep walking around disrespecting me. This is Sodom and Gomorrah, man, and I'm not with it.
Sodom and Gomorrah? Hold on, how do the guards not come? This is the guard right now. Like, oh, that's just a female unit. It's interesting that girls fight like that. They just grab the hair. Yeah, grab her hair.
Here, when you're in a fight, you're not in that fight alone. Your whole room is in the fight. I was just watching, and I understand why my husband is so aggressive. I get everything that he was going.
They're in there.
You're gonna regret this.
Really wasn't a fight, it was a beatdown where the gang members protect each other. When there are gangland things going on, that's not the time to interject.
I guess not.
If T-Bone was on the street, he would have killed that man. I promise you that. He would have ended his life.
After people looked at me, I'm like, yo, I was nervous. So I just needed to stay away and just like regroup myself.
The pod. Is that like the bubble?
And one thing about jail, you can always expect a fight to go down.
Four gangbangers surrounded the cell and wouldn't let anybody in. And that's how that goes. The gang members protect each other.
It's interesting they don't close the cell because they're not that confident.
I had no idea.
You could literally just close the pin, is what it's called.
Why are they not trying to stop this? I was nervous. And be. I know.
I rolled that phone. I was like, no, there was other jumping. I came in the shower.
You lying.
Somebody jumped me in the fucking shower. Didn't do shit though. He walked up fucking bleeding.
I don't want to see Bucci hurt.
I was gonna act pissed off that I just got off the phone just to throw them off.
I'm. Very helpful people, talking to people.
Oh, that's video shit.
You guys know Henry from Miniphysics, right? Well, he and I just made a video on a certain quantum mechanical topic, Bell's inequalities.
It's a really mind-warping topic that not enough people know about, and even though it's a quantum thing, it's based on some surprisingly simple math, and you should definitely check it out.
For this video, we have in mind those of you who actually want to learn some quantum mechanics more deeply. And obviously, it's a huge topic, nowhere near the scope of a single video, but the question we asked was, what topic could we present that's not meant to be some eye-catching piece of quantum weirdness, but which actually lays down some useful foundations for anyone who, wants to learn this field? What topic would set the right intuitions for someone before they dove into, say, the Feynman lectures? Well,
let's actually see the Feynman lecture. I don't think I've ever looked that up.
Is light. Specifically, if you want to learn quantum, you have to have an understanding of waves and how they're described. To build
complex exponentials. Boom, waves.
The energy in a purely classical wave and the probabilities that govern quantum behavior.
In fact, we'll actually spend most of the time talking through the pre-quantum understanding of light, since that sets up a lot of the relevant wave mechanics. The thing is, a lot of ideas from quantum mechanics, like describing states as superpositions of various amplitudes and phases, come up in the context of classical waves in a way that doesn't involve any of the quantum weirdness people might be familiar with. This also helps to appreciate what's actually different in quantum mechanics, namely certain restrictions on how much energy these waves can have, how they are measured, and quantum entanglement, though we won't cover entanglement in this video. So we'll start with the late 1800s understanding
with the velocity
and the electromagnetic field.
Phase shift.
Here, let's break that down a bit. The electric field is a vector field, and that means every point in space has some arrow attached to it indicating the direction and strength of the field. Now, the physical meaning of those arrows is that if you have some charged particle in space, there's going to be a force on that particle in the direction
Hold
of
on,
the
that's
arrow,
actually...
and it's proportional to the length of the arrow and the specific charge of the particle. Likewise, the magnetic field, it's another vector field, where now, the physical meaning of each arrow is that when a charged particle is moving through that space, there's going to be a force perpendicular to both its direction of motion and to the direction of the magnetic field. And the strength of that force is proportional to the charge of the particle, its velocity, and the length of the magnetic field arrow.
For example, a wire with a current of moving charges next to a magnet is either pushed or pulled by that magnetic field. A kind of culmination of the 19th century physics understanding of how these two fields work are Maxwell's equations, which among other things describe how each of these fields can cause a change to the other.
Specifically, what Maxwell's equations tell us is that when the electric field arrows seem to be forming a loop around some region, the magnetic field will be increasing inside that region, perpendicular to the plane of the loop. And symmetrically, such a loop in the magnetic field corresponds to a change in the electric field within it, perpendicular to the plane of the loop. Now, the specifics for how exactly these equations work is really beautiful and worth a full video.
Yeah, they're very simple.
But all we
Just
need to know
differential
for now
equations.
is that one natural consequence of this mutual interplay in how changes to one field cause changes to the other in its neighboring regions is that you get these propagating waves where the electric field and magnetic fields are oscillating perpendicular to each other and perpendicular to the direction of propagation. When you hear the term electromagnetic radiation, which refers to things like radio waves and visible light, this is what it's talking about, propagating waves in both the electric and magnetic fields.
Of course, it's now almost mainstream to know of light as electromagnetic radiation, but it's neat to think about just how surprising this was in Maxwell's time. That these fields that have to do with forces on charged particles and magnets not only have something to do with light, but that what light is a propagating wave as these two fields dance with each other, causing this mutual oscillation of increasing and decreasing field strength.
If this is a visual, let's take a moment to lay down the math used to describe waves. It'll still be purely classical, but ideas that are core to quantum mechanics, like superposition, amplitudes, phases, all of these come up in this context. And I would argue with a clearer motivation for what they actually mean. Take this wave and think of it as directed straight out of the screen, towards your face. And let's go ahead and ignore the magnetic field right now, just looking at how the electric field oscillates. And also, we're only going to focus on one of these vectors oscillating in the plane of the screen, which we'll think of as the XY plane. If it oscillates horizontally, like this, we say that the light is horizontally polarized. So the Y component of this electric field is 0 at all times, and we might write the X component as something like cosine of 2 pi times ft, where f represents some frequency and t is time. So if f was 1, for example, that means it takes exactly 1 second for this cosine function to go through a full cycle.
This cosine is the real part of the imaginary exponential.
Lower frequency.
It's just what you do. You just say it's real. You just take the complex exponential and you take the real part of the imaginary part, and you take away the I, and that's how you do math with waves.
That would mean it takes more
just use the
time
complex
for the cosine
exponential
to go through its full cycle. As the value t increases, the inside of this cosine function increases more slowly. Also, we're going to include another term in here, phi, called the phase shift, which tells us where this vector is in its cycle at time t equals 0. You'll see why that matters in just a moment. Now by default, cosine only oscillates between -1 and 1. So let's put another term in front, a, that gives us the amplitude of this wave. One more thing, just to make things...
Okay, I don't really care. Okay, KT. This guy derives the... the change of pressure with respect to rho.
Things look a little more like they often do in quantum mechanics. Instead of writing it as a column vector, like this, I'm going to separate it out into two different components using these symbols called kets. This ket here indicates a unit vector in the horizontal direction, and this ket over here represents a unit vector in the vertical direction.
I didn't know that.
If the light is vertically polarized, meaning the electric field is wiggling purely in the up and down direction, its equation might look like this, where the horizontal component is now 0, and the vertical component is a cosine with some frequency, amplitude, and a phase shift. Now if you have two distinct waves, two ways of wiggling through space over time that solve Maxwell's equations, then adding both of these together gives another valid wave, at least in a vacuum. That is, at each point in time, add these two vectors tip to tail to get a new vector. Doing this at all points in space and all points in time gives a new, valid solution to Maxwell's equations. At least this is all true in a vacuum.
This is because Maxwell's equations in a vacuum are what's called linear equations. They're essentially a combination of derivatives acting on the electric and magnetic fields to give 0. So if one field F1 satisfies this equation, and another field F2 satisfies it, then their sum, F1 plus F2, also satisfies it, since derivatives are linear. So the sum of two or more solutions to Maxwell's equations is also a solution to Maxwell's equations.
And there's infinitely many.
This new wave is called a superposition of the first two. And here, superposition essentially just means sum, or in some contexts, weighted sum, since if you include some kind of amplitude and phase shift in each of these components, it can still be called a superposition of the two original vectors. Now right now, the resulting superposition is a wave wiggling in the diagonal direction. But if the horizontal and vertical components were out of phase with each other, which might happen if you increase the phase shift in one of them, their sum might instead trace out some sort of ellipse. And in the case where the phases are exactly 90 degrees out of sync with each other, and the amplitudes are both equal, this is what we call circularly polarized light. This, by the way, is why it's important to keep track not just of the amplitude in each direction, but also of the phase. It affects the way the two waves add together. That's also an important idea that carries over to quantum, and underlies some of the things that look confusing at first. And here's another important idea. We're describing waves by adding together the horizontal and vertical components, but we could also choose to describe everything with respect to different directions. I mean, you could describe waves as some
Spin up and
superposition
spin
of
down.
the diagonal and the anti-diagonal directions. In
Just
that
what I do
case,
broadcast
vertically
for.
polarized light would actually be a superposition of these two diagonal wiggling directions, at least when both are in phase with each other and they have the same magnitude. Now, the choice of which directions you write things in terms of is called a basis. And which basis is nicest to work with? Well, that typically depends on what you're actually doing with the light. For example, if you have a polarizing filter, like that from a set of polarized sunglasses, the way these work is by absorbing the energy from electromagnetic oscillations in some particular direction. A vertically oriented polarizer, for example, would absorb all of the energy from these waves along the horizontal directions. At least classically, that's how you might think about it. So, if you're analyzing light and it's passing through a filter like this, it's nice to describe it with respect to the horizontal and vertical directions. That way, what you can say is that whatever light passes through the filter is just the vertical component of the original wave.
Indeed.
But if you had a filter oriented, say, diagonally, well, then it would be convenient to describe things as a superposition of that diagonal direction and its perpendicular anti-diagonal direction.
I feel like that's unnecessary.
These ideas will carry over almost word for word to the quantum case. Quantum states, much like this wiggling direction of our wave, are described as a superposition of multiple base.
I think the entirety of quantum mechanics is just applying the properties of light to particles. And I said this. Let me see if I can search for it. Holy shit. Light. Doesn't work, okay. When the fuck did I say it? Did I say it is the question. Huh. Well, it's around here. It's like on the brink of this. Apparently nobody's subscribing to Netflix anymore because it's shit. Okay, whatever. I don't really care.
States, where you have many choices for what base states to use. And just like with classical waves, the components of such a superposition will have both an amplitude and a phase of some kind. And by the way, for those of you who do read more into quantum mechanics, you'll find that these components are actually given using a single complex number rather than a cosine expression like this one. One way to think of this is that complex numbers are just a very convenient and natural mathematical way to encode an amplitude and a phase with a single value. That can make things a little confusing because it's hard to visualize a pair of complex numbers, which is what would describe a superposition of two base states. But you can think about the use of complex numbers throughout quantum mechanics as a result of its underlying wavy nature, and this need to encapsulate the amplitude and the phase for each direction.
Okay, just one quick point before getting into the quantum. Look at one of these waves and focus just on the electric field portion like we were before. Classically, we think about the energy of a wave like this as being proportional to the square of its amplitude. And I want you to notice how well this lines up with the Pythagorean theorem. If you were to describe this wave as a superposition of a horizontal component with amplitude ax and a vertical component with amplitude ay, then its energy density is proportional to ax squared plus ay squared. And you can think of this in two different ways. Either it's because you're adding up the energies of each component in the superposition, or it's just that you're figuring out the new amplitude using the Pythagorean theorem and taking the square. Isn't that nice?
In the classical understanding of light, you should be able to dial this energy up and down continuously however you want by changing the amplitude of the wave. But what physicists started to notice in the late 19th and early 20th centuries was that
Waves
this
don't
energy
work.
actually seems to come in discrete amounts. Specifically, the energy of one of these electromagnetic waves always seems to come as an integer multiple of a specific constant times the frequency of that wave. We now call this constant Planck's constant, commonly denoting it with the letter h. Physically, what this means is that whenever this wave trades its energy with something else, like an electron, the amount of energy it trades off is always an integer multiple of h times its frequency. Importantly, this means there is some minimal non-zero energy level for waves of a given frequency, hf. If you have an electromagnetic wave with this frequency and energy, you cannot make it smaller without eliminating it entirely. That feels weird when the conception of a wave is a nice continuously oscillating vector field. But that's not how the universe works, as late 19th and early 20th century experiments started to expose. In fact, I've done a video about this called The Origin of Quantum Mechanics.
However, it's worth noting that this phenomenon is actually common in waves when they're constrained in certain ways, like in pipes or instrument strings, and it's called harmonics. What's weird is that electromagnetic waves do this in free space, even when they're not constrained.
And what do we call an
Depends on your
electromagnetic wave with this minimal possible
definition
energy?
of...
A photon.
But like I said, the math used to describe classical electromagnetic waves carries over to describing a photon. It might have, say, a 45-degree diagonal polarization, which can be described as a superposition of a purely horizontal state and a purely vertical state, where each one of these components has some amplitude and phase. And with a different choice in basis, that same state might be described as a superposition of two other directions. All of this is stuff that you would see if you started reading more into quantum mechanics. But this superposition has a different interpretation than before, and it has to. Let's say you were thinking of this diagonally polarized photon kind of classically, and you said it has an amplitude of 1 unit for some appropriate unit system. Well, that would make the hypothetical amplitudes of its horizontal and vertical components each the square root of 1/2. And like Henry said, the energy of a photon is this special constant h times its frequency. And because in a classical setting, energy is proportional to the square of the amplitude of this wave, it's tempting to think of half of the energy as being in the horizontal component, and half of it as being in the vertical component. But waves of this frequency cannot have half the energy of a photon. I mean, the whole novelty of quantum here is that energy comes in these discrete, indivisible chunks.
Quantized.
So these components, with an imagined amplitude of 1 over the square root of 2, could not exist in isolation. And you might wonder what exactly they mean. Well, let's get experimental about it. If you were to take a vertically oriented polarizing filter and shoot this diagonally polarized photon right at it, what do you think would happen? Classically, the way you'd interpret this superposition is that the half of its energy in the horizontal direction would be absorbed. But because
it's
energy comes in
quantized.
these discrete photon packets, it either has to pass through with
just has
all
a
of its
non-
energy or get absorbed entirely. And if you actually did this experiment, about half the time the photon goes through entirely.
Holy
and about
fuck,
half
that's
the time
cool.
it gets absorbed entirely. And it appears to be random whether a given photon passes through or not. If it does pass through, forcing it to make a decision like this actually changes it so that its polarization is oriented along the filter's direction. This is analogous to the classic Schrodinger's cat setup. You have something that's in a superposition of two states, but once you make a measurement of that superposition, forcing it to interact with an observer in a way where each of those two states would behave differently, from the perspective of that observer, this superposition collapses to be entirely in one state or entirely in another, dead or alive, horizontal or vertical. One pretty neat way to see this in action, which Henry and I talk about in the other video, is to take several polarized sunglasses, or some other form of polarizing filters, and start by holding two of them between you and some light source. If you rotate them to be 90 degrees off from each other, the light source is blacked out completely, or at least with perfect filters it would be, because all of the photons passing through that first one are polarized vertically, so they actually have a 0% chance of passing a filter oriented horizontally. But
Perfectly
if you insert a third filter oriented at a 45-degree angle between the two, it actually lets more light through. And what's going on here is that 50% of the photons passing that vertical filter will also pass through the diagonal filter. And once they do, they're going to be changed to have a purely diagonal polarization. And then once they're in that state, they have a 50-50 chance of passing through the filter oriented at 90 degrees. So even though 0% of the photons passing through the first would pass through that last if nothing was in between, by introducing another filter, 25% of them now pass through all three. Now that's something that you could not explain unless that middle filter forces the photons to change their states. And that experiment, by the way, becomes all the weirder when you dig into the specific probabilities for angles between 0 and 45 degrees. And that's actually what we talk about in the other video. For example, one specific value we focus on there is the probability that a photon whose polarization is 22.5 degrees off the direction of a filter is going to end up passing through that filter. Again, it's helpful to think of this wave as having an amplitude of 1, and then you'd think of the horizontal component as having amplitude sine of 22.5 degrees, which is around 0.38, and the vertical component would have an amplitude cosine of 22.5 degrees, which is around 0.92. Classically, you might think of its horizontal component as having energy proportional to 0.38 squared, which is around 0.15. Likewise, you might think of the vertical component as having an energy proportional to 0.92 squared, which comes out to be around 0.85. And like we said before, classically, this would mean if you pass it through a vertical filter, 15% of its energy is absorbed in the horizontal direction. But because the energy of light comes in these discrete quanta that cannot be subdivided, instead what you observe is that 85% of the time, the photon passes through entirely, and 15% of the time, it gets completely blocked.
Which pops out of the Schrodinger equations, the Hamiltonian.
Now I want to emphasize that the wave equations don't change. The photon is still described as a superposition of two oscillating components, each with some phase and amplitude. And these are often encoded using a single complex number. The difference is that classically, the squares of the amplitudes of each component tells you the amount of that wave's energy in each direction. But with quantized light, at this minimal non-zero energy level, the squares of those amplitudes tell you the probabilities that a given photon is going to be found to have all of its energy in one direction or not. Also, these components could still have some kind of phase difference. Just like with
very true
waves,
indeed.
Photons can be circularly polarized. And there exist polarizing filters that only let through photons that are polarized circularly, say in the clockwise direction. Or rather, they let through all photons probabilistically, where the probabilities are determined by describing each one of those photons as a superposition of the clockwise and counterclockwise states, and then the square of the amplitude of the clockwise component gives you the desired probability.
Photons are, of
Indeed,
course,
bro.
just one quantum phenomenon. One where
That
we
just makes
initially
total
understood it
sense.
as a wave thanks to Maxwell's equations, and then as individual particles, or quanta, hence the name quantum mechanics. But as many of you well know, there's a flip side to this, where many things that were understood to come in discrete little packets, like electrons, were discovered to be governed by similar wavy quantum mechanics. In cases way more general than this one photon polarization example, quantum mechanical states are described as some superposition of multiple base states, and the superposition depends on what basis you choose. Each component in this superposition is given with an amplitude and a phase, often encoded as a single complex number, and the need for this phase arises from the wave nature of these objects. As with the photon example, the choice of how to measure these objects can determine a set of base states, where the probability of measuring a particle to be in one of these base states is proportional to the squares of the amplitudes of these numbers. It's funny to think, though, that if
Fuck.
the wavy nature of electrons and other particles was discovered first, we might instead refer to the whole subject as harmonic
You have
mechanics or something like that,
517
since the weirdness there
messages?
is not that waves come in discrete units, but that particles are governed by wave equations.
This video was supported in part by Brilliant, and as viewers...
Indeed. Oh shit. Yeah, you got 517 messages in my chat. Isn't that freaking sweet? Okay. Really? Holy shit. I don't know how old my original Twitch account is. Is this even my account? I don't even know. I think it might be this one. Oh, it doesn't say. That's not my original account. I made a few accounts. This is just the last one that I made. Fucking holy fucking balls, I was high. I should take this down, eh? Yeah, I know. I don't really care though. I just fucking... Oh god. It's cringe. I know this guy. Well, I am young in the clip. I was like 26. I'm 29 now. It's 3 years ago. What? What? It's almost exactly 3 years ago. It's a little bit under, but... Okay, can I just restart the stream real quick? I need to rename it. May, I believe. Because that's when... Okay.